Hello everybody. In this lecture today we continue that how to design tunable devices and in turn reconfigurable circuits, and we discussed in previous lectures what are the factors important for tuning a devices and reconfigurable circuits, and today here we are going to discuss Thermo-Optic tuning. That is a very important tuning mechanisms and switching mechanism for especially for silicon photonic circuits. So, first of all I will discuss about the Thermo-Optic phase shifters. So, how to design a Thermo-Optic phase shifters, what are the figure of merits, and how to optimize design parameters. Then I will be discussing using that Thermo-Optic phase shifters one can design optical switch on chip or integrated optical switching devices. And finally, again using same phase shifters, Thermo-Optic phase shifters, we can also reconfigurable resonant devices like micro ring resonators to operate different operating wavelengths. So, that is how we call it as a Thermo-Optic wavelength detuning. So, first Thermo-Optic phase shifters. As usual, we have just categorized two different type of Thermo-Optic phase shifters, type 1 and type 2. Also it is clear that from the name Thermo-Optic, meaning you have to apply some thermal energy, then some optical property will be changing. In this case, phase of the guided mode, we mean to say phase of the guided mode will be changed, and because of the thermal power. Silicon itself is a very good Thermo-Optic material. So, if you just raise the temperature, refractive index will be increased. So, that is the mechanism, that is the principle we follow to design Thermo-Optic phase shifters. In this design, if you see, we have given a design of waveguide design, cross section, re-waveguide structure, where you have a finite W value, width, waveguide width, and device layer thickness, this one, and then of course this slab thickness, small h. Okay. Re-waveguide structure, it can be, this can be also 0, okay. And then type 1, you can have top cladding, you should have in this type 1 design, you should have a silicon dioxide top cladding. Instead of air, you use silicon dioxide, you grow silicon dioxide up to a certain level, and then after a D1 height from the waveguide surface, you deposit a heater, that is nothing but resistive heater. It can be a some metal like tungsten, like titanium, nickel, so on. So, here in this case the width of the heater, it is defined by WH, and thickness TH. Depending on the thickness and width, you can have the resistance of the micro heater. For example, resistance of the micro heater, you know, that can be rho resistivity, what is the resistivity of the deposited material, and length proportional to length divided by A, WH multiplied by TH. So, that is the resistance. So, this is for sure thickness, actually lower the thickness, resistance will be increased, or width lower, resistance will be increased. So, this is cross section. I will show you that this L actually, as it should be, the micro heater should be parallel to the waveguide surface, and as long as L runs for the micro heater, that is called, that will be called as a waveguide phase shifters. Why it is phase shifter, again I will discuss. And on the top of it, again you can also have some kind of silicon dioxide box layer, again you deposit to passivate everything, and where you want to make a contact, you can open the oxide and you can do it easily from bonding, wire bonding, or making some contact out of the device. So, if you pass the current through this one, microheater from one end to another one. Then because of the joule heating I square R, you can imagine that joule heating heat energy that will transfer through the oxide to the waveguide, silicon waveguide, and because of the higher thermal capacity and conductivity in the silicon temperature will be increased compared to your surrounding oxide. So, as the temperature increases, you know that bulk silicon actually have a Thermo-Optic coefficient equal to 1.86 into 10 to the power minus 4 per Kelvin. Okay. And also you can think of that cladding NiSiO2 by dt, you can also have that is in the order of 10 to the power minus 5 or so. It is actually less than 10 to the power minus 5 or so per Kelvin. So, mainly your silicon core will be heated. If you are just doing some resistive heating by sending current through the across the heater, then it will be heated. So, once it is heated, then refractive index change, as you know, it will be actually can be expressed for a given waveguide effective index N effective by dt. You can see that normally this dN effective in principle more or less will show that dN by dt for silicon case it should be NSi by dt normally. So, if you are raising temperature of delta T, then you can find out how much refractive index change you can actually raise in the waveguide structure. That is one type. And second type is you should have a waveguide design where the slab not equal to 0 and top of the slab with a safe distance, we can call it dii, and this is di vertical distance, it is lateral distance dii. Safe distance you can deposit a metal heater, identical metal heater. Because why I am saying safe distance, because whenever your mode is just confined here, this mode evanescent field should not penetrate it towards the metal, because below the metal if some field exists and that field can be attenuated by this metal, because metal has a reasonably high sigma, that sigma contributes at certain loss. So, this type of heater also cross sectional view also people realized, and we can show that there are some kind of pro and cons for both type of heater configuration. And in this case you can have top cladding silicon dioxide or you can keep it just bare. Okay. So, here also when heat is dissipated, because silicon is dissipated because of the joule heating, then this heat energy can be conducted. This is the conducting path. Silicon is highly conducting, thermally conducting compared to silicon dioxide, and it will conduct and it can raise the temperature of the waveguide, and by the same effect you can see this temperature will be raised, refractive index will be changed, and you can have some kind of phase shifter depending on the length. So, these two type of heaters mostly used in CMOS industry, and also lot of experiments carried using these two type of Thermo-Optic phase shifters. There are many other type of phase shifters are available, but they are still in a nascent stage. So, they need to be matured. So, I am not discussing in this course all those type of phase shifters, particularly Thermo-Optic phase shifter with different configurations, but with this two configuration you can get a better idea and overall working principle. Let us see how it works. So, let me just show you the top view. So, this is your waveguide where your light can be launched and your mode is excited and it will be propagated through here and it will be going out through that. And in the top you can have this heater or this heater along the length, it is shown something like that. This is your heater length, you can say L phase shifter. Okay, here it is shown length of the phase shifter, we can say. Okay. This can be waveguide, and this waveguide can be any form. It can be bent structure, it can be ring type of waveguide structures, but for the simplicity simple discussion purpose, we have just considered here a straight waveguide configuration. So, this waveguide can be this waveguide and micro heater configuration can be type 1 and type 2. Just for perspective view, I have shown just outside the waveguide top view. So, this is the waveguide top view and also micro heater top view. This micro heater can be directly onto the top of the waveguide here as shown here. Okay. So, now let us see what happens. So, suppose LPS, that means the length of the phase shifter, where you are sending a current, you are making a contact here. For example, you are just connecting a voltage source here, and then this will send a current because it is R, some micro heater resistance will be there. So, you can think of micro heater current is actually V by R each. Okay. Whatever the source you are giving, depending on the current will be there, and this current in turn will cause some kind of joule heating of this heater, and that heat energy will be transferred to the waveguide. So, if it transferred to the waveguide, some refractive index will take place, and we have seen that the phase shift for a phase shifter length of LPS delta phi equal to 2 pi by lambda. Lambda is the operating wavelength. So, if your device is operating at lambda, input laser, you are launching here lambda, okay, 2 pi by lambda, and delta N effective, we know that beta equal to 2 pi by lambda N effective, right, and phase normally equal to 2 pi by lambda N effective L. So, if L is fixed, lambda is fixed, delta phi must be equal to 2 pi by lambda times delta N effective times L. That is what it is mentioned here. L is the phase shifter. So, then 2 pi by lambda times delta N effective. This delta N effective change, how it is happening? Because of the thermal effect, and Thermo-Optic coefficient we have del N effective by del T, and delta T is the temperature rise in the waveguide core, for example. So, this is your accounting as a delta N effective and multiplied by LPS. Now, what you do? You are trying to get how much temperature rise required to have a pi phase shift. So, if you are just putting delta phi equal to pi, then you can just calculate delta T pi. Whatever the temperature rise required, we call it as a delta T pi. With a simple simplification, with simple algebra, you can just find out delta T pi. That means that is the temperature rise required in the waveguide section, cross section, so that you can get pi phase shift for a waveguide phase shifter of length LPS. So, that would be lambda by lambda over 2 LPS, and this inverse of del N effective by del T. Okay, this is straightforward. This is the temperature rise required for pi phase shift. We are just putting delta phi equal to pi, nothing else. So, now let us assume, just to see quantitative how much temperature increment required for pi phase shift. Let us assume operating wavelength is lambda equal to 1550 nanometer, and phase shifter length is 250 micrometer. Just sufficiently long we have considered. It can be 10 micrometer, it can be 5 micrometer, it can be anything, depending on that other parameter has to be adjusted. So, lambda equal to 1550 nanometer, phase shifter length is about 250 micrometer, and del N effective by del T, we have just assumed that 2 times 10 to the power minus 4. Typically, it is between 1.7 to 1.9 or so into 10 to the power minus 4 per Kelvin. Typically, it is there, we just consider T. So, now if we just substitute this lambda value here, this LPS value here, this delta N effective here, then we find delta T pi equal to 15.5 Kelvin. So, that means if your phase shifter length is considered to be 250 micron and you want to have a Thermo-Optic phase shift of pi, then your waveguide core needs to be heated to a temperature higher than the room temperature of about delta T pi equal to 15.5 Kelvin. So, you should keep in mind that if this length is more, then your temperature rise can be lower. Let us consider LPS equal to say just 25 micrometer instead of 250. In that case, delta T pi will be equal to 155 Kelvin. That means your waveguide core temperature units to increase by 155 Kelvin. So, it is clear that longer the length, you do not need to, you can actually raise the temperature lower to have a desired phase shift in the waveguide or for the guided mode. Okay. Now, let us see. This is what I commented here. Longer the waveguide phase shifter, smaller is the temperature rise requirement in the waveguide core. For a given phase shifter, I want pi phase shift, that is how we can calculate. This is straightforward. But challenge is that how you can raise this temperature. Delta T equal to 15.5 or 155, or even if you want, for example, even 10 micron or so, then it will be even higher temperature requirement, maybe up to 200 Kelvin. People have shown that this temperature can be increased up to more than 600, 700 Kelvin or so. So, that you have to raise the temperature such that your resistor micro heater should not be burnt and also your waveguide should not be destroyed. That you have to take care how much temperature you are raising. And also you should keep in mind, we will be discussing later, that while heating in one waveguide, there should not be a thermal crosstalk to another neighboring waveguide or neighboring devices. It should not disturb other neighboring devices. So, thermal crosstalk should be minimized. So, you should keep in mind that whenever you are designing this device Thermo-Optic phase shifter, and if you want to raise a very high temperature, you should be very much careful that this high temperature, because of the high temperature there will be some kind of thermal conduction in the surrounding region. So, surrounding region other devices should not be disturbed, so that they should be kept at a separate safe distance, I mean to say. Okay. So, now let us see. You are not applying voltage here, you are applying voltage here in the heater. So, this is for example, you are having V, and then this one you are just making with respect, that potential difference you are making with respect to the ground here, you can connect the negative terminal here. So, current will be flowing. So, in that case temperature rise. So, temperature rise will be how much? Suppose I current is flowing, I amount of current is flowing. So, total heat energy will be dissipated by this resistor of resistance RH equal to I square RH. Now, this temperature rise must be proportional to I square RH divided by LPS. That means, how much energy we have just normalized with the length of the phase shifter. That means, how much energy we are dissipating per unit length here. If this per unit length heat dissipation is more, temperature rise will be more. Per unit length heat dissipation is less, temperature rise will be less. That is why we are writing proportional. So, I square RH, instead of that I can write VH square RH. Instead of this one, if I write VH, potential difference, VH square divided by RH LPS. So, I square RH, that will be equal to VH square by RH. So, if you have a voltage source, you can use this equation. If you have a current source, you can use this equation. This can be written as, you see, normally this power, this is the total power dissipation and divided by LPS. LPS means phase shifter length. So, I can write that power dissipation per unit waveguide phase shifter is PW we define. And we just use a different term, that is a proportionality constant SH, that is we call it as a thermal sensitivity, because you see delta Ts equal to SHPW. How much power you are actually dissipating per unit length, actually if SH is higher, that means your temperature rise will be higher. If certain device architecture giving SH less, then delta Ts will be less for a given input power. Okay. So, here we call it as a delta Ts is the steady state temperature of the phase shifter. That means, you are applying a DC voltage, and DC current source, then whatever temperature rise happen starting from the beginning to a certain steady state condition, we say that temperature rising delta Ts amount of temperature rising is happening. Okay. So, Pw as usual I mentioned is the power consumed per unit length of the phase shifter. So, total power, it is power you are just how much you are spending for the microheater. It does not mean that all the heat energy is being used up, because there will be some kind of heat conduction, radiation, dissipations depending on the surrounding ambience. Okay. So, depending on the surrounding ambience, actually this temperature rise will take place. The surrounding ambience and physical parameters, waveguide parameters, everything that actually defines, that actually decides how good is the sensitivity SH, high or low. Okay. So, next thing is that, okay, this is we call that steady state temperature rise, but normally if you want to use that phase shifter for a certain duration of time, or you want to make certain kind of switch, we will be discussing little while later. So, in that case it is very important how fast you can raise the temperature, how fast you can actually cool it down, the waveguide. So, that is being decided, that is actually decided by another constant we will be calling, like SH we can call there another parameter, that is another figure of merit called thermal time constant of the phase shifter. Phase shifter, when I say phase shifter, that is actually combined structure, waveguide plus microheater and surrounding region, cladding, etc., slab heights, everything is included. Okay. So, if this is the case, then we know that steady state temperature is delta Ts and how it increase. So, if you just see the temperature rise, normally it is time, and then initially as a function of time, if you switch on some step function, for example, as a voltage source, then what happens, if this is your delta Ts, then you can have that delta Ts, it will be slowly it will be just reaching to delta Ts, right. And you know, if you are cooling down, slowly again it will be cooling down exponentially. So, this rise time and this fall time, most of the time actually it is almost equivalent, but it depends on how close microheater you are considering, you are integrating, depending on that how fast it can rise. But whenever cooling down, that time this microheater closeness does not matter, it depends on your everything, conductivity, surrounding regions, everything. So, that is why sometimes this rise time and fall time can be different. But for the discussion purpose here, we consider that this tau Th is the rise time, because that is actually the ultimate thing you can get, you can actually estimate very accurately, because that is the proximity of microheater, etc., and the conductivity, thermal heat capacitance, everything controls that one. So, normally this is actually 1 minus e to the power Th. This can be actually following like a T by tau Th thermal constant, and this can follow this function. Okay. So, it saturates, and this is actually called thermal constant, how fast it is cooling, maybe how fast the temperature rise or differential temperature is dropped to 1 by E, 1 over E, that is actually thermal constant, standard way what we discuss normally. Fine. Next thing is that how you can define normally this tau Th. Normally, you know, if you have a RC circuit and anything voltage rise and voltage discharging, normally we say that the time constant T by RC. R is the resistance, C is the capacitance for a RC circuit, the rise time, fall time, or the time constant is normally RC, that you know from the very basic course of electrical circuit, right. So, similarly, here also instead of electrical circuit consisting of resistance and capacitance, here also what you can consider, resistance 1 by R, of course, you know that is conductance is responsible, current conductance G, or whatever things you consider. In this case, we can also have, whenever there is a thermal source through the material, that thermal energy, how fast it can conduct, how good conductivity is the surrounding material. So, that conductance or the inverse of resistance, thermal resistance, inverse of thermal resistance is thermal conductance, or inverse of thermal conductance is thermal resistance. So, that means like RC circuit, whatever conductance is responsible or resistance responsible, here also thermal constant is also responsible, how fast it is cooling or how fast it is actually heating up, that actually depends on the conductance, thermal conductance. When I say that thermal conductance, this is actually we are showing that heat conductance or thermal conductance we are making. And another thing is the heat capacitance. You know, heat capacitance means how for a given for 1 degree temperature rise how much heat energy is required, and if it is 1 gram then it is a specific heat, otherwise if it is a just a bulk material how much energy is required to raise the temperature of the substrate of the material up to 1 degree, that is actually called heat capacitance. So, that means this can be considered equivalent to capacitance and this can be considered equivalent to 1 over resistance for an electrical circuit, analogous to electrical circuit. So, that is the reason you see I can write that thermal constant tau thermal equal to H is equivalent to capacitance and inverse of G. That means inverse of thermal conductance, that is actually resistance. So, it is like a RC. Thermal constant in normally tau equal to RC in electrical circuit, here also it is something like that, H is equivalent to C, thermal capacitance instead of electrical capacitance, and then you have thermal conductance, inverse of thermal conductance is thermal resistance. So, you can actually define thermal constant tau H equal to H by G. So, you need to know the entire system, what is H value and what is the G value of these systems. You know, this phase shifter is a part of a large integrated circuits. So, it is not so easy to find out, it is actually stupid to find out heat capacitance for the entire chip or conductance for the entire region. Rather, we can just try to define distributed heat capacitance and distributed conductance. So, how that can be done? You can define this H divided by LPS. So, you just consider the length of your phase shifter, you normalize it. Similarly, denominator also you can normalize with phase shifter, and that is considered HW and GW. HW, that means HW waveguide phase shifter, I mean to say HW is equal to capital H by LPS. Whatever effective heat capacitance you have for the system surrounding the microheater, that you normalize with the LP, and that can be considered as a distributed heat capacitance of the microheater waveguide phase shifter system. So, we can say this is a characteristics heat capacitance, distributed heat capacitance. Similarly, you can define distributed conductance, that means overall conductance per unit length, you can distribute over entire phase shifter LPS. So, GW. So, this can be written, that means instead of this one I can write the per unit length how much capacitance we are normalizing, just nothing else, normalizing with the length, that will be actually thermal constant. So, if you can quantify HW and GW by experimental means or by very good theoretical model, then you can predict that whatever the thermal constant is possible, and that thermal constant, you know, that is very important. It actually decides how fast you can heat it up and how fast you can cool it down. So, that is how you can think of how fast, what would be the modulation speed, Thermo-Optic modulation speed, that entirely depends on tau value, thermal constant. Okay. So, next thing is that since this delta Ts is directly related to the total consumed electrical power P, that means total consumed electrical power, that is nothing but I square RH or V square VH square by RH. So, this value or this value, this is the total value, this we define as a total electric power consumed, okay, and conductance G, then normally it can be shown that temperature rise multiplied by conductance, temperature rise multiplied by conductance that actually equal to your power consumption, electrical power consumption, PE. We can write like that, if we can model like that. Okay. So, then what you can do here, this PW, that means you just divide left hand side by LPS and right hand side also LPS. That means left hand side will give you PW, right hand side delta TS GW. That means you can remember that this PW now, that means power consumed per unit length of the waveguide phase shifter is actually help how much temperature rise in steady state, that decides by how good it is the conductance. So, it is clear that if I am using say 1 milliwatt per micrometer of waveguide phase shifter. So, the temperature rise will be more for that given power if GW is less, conductance is less. Clearly, if thermal conductivity is less surrounding region, whatever energy if you supply that will be actually helpful to raise the temperature. So, that is how it is justified. So, you would like to have lower conductivity, lower conductance, thermal conductance to dispense of the lower power to get a desired phase shift. Okay. So, that is very important. Now, you see, that is why we call it, we define say sensitivity here, delta Ts is proportional to Pw. So, if we just compare this one and this one, this equation and this equation, then we can find that sensitivity equal to 1 over GW, whatever sensitivity we are getting. That means, higher the conductivity, sensitivity will be lower. Higher the thermal conductance, lower is the sensitivity. Smaller the conductance, sensitivity high. What sensitivity means? It is kind of capacitance, like how good it is, temperature rise is happening. So, this is a different way of modeling a waveguide phase shifter. Good. Next thing is that figure of merit. So, figure of merit, you want SH to be as high as possible and you want tau TH should be as low as possible. So, this is one figure of merit we want. Good, sensitivity should be good for a given power, the temperature rise should be as high as possible. So, that you do not need to spare lot of electrical power to get a desired phase shift. Similarly, you want very fast switching, very fast temperature rise, tau TH should be as small as possible. Okay. So, in that case we can define a figure of merit something like that, we can call that is actually SH by tau H. You have to maximize this figure of merit. Maximizing that figure of merit means you have sensitivity is higher and thermal constant is lower. So, you can do very high temperature rise and in a quicker time interval. That is why it is called figure of merit. So, this figure of merit will be SH by tau H. Now, you know SH is 1 over g omega, right. Tau H you know H omega means W, I would say W, HW by GW. So, ultimately the figure of merit, if you see, that depends on 1 over HW, heat capacitance, distributed heat capacitance. So, distributed heat capacitance should be smaller. That means, your system you should design such that you need to have very low, very low heat capacitance. That means, very low power needed to raise the temperature. That is a different way of just explaining, modeling your Thermo-Optic phase shifter. Good. So, now we discuss phase shifter related, how fast, what is the power requirement, what is the design requirement, critical things we discussed. Now, using that type of Thermo-Optic phase shifter, we can actually demonstrate a switch, integrated optical switch. Integrated optical switch is what? Suppose you want to switch from one port to another port, entire power, entire signal from one port to another port. We know that Mach-Zehnder interferometer, working principle of Mach-Zehnder interferometer, it has a 2 port, 1, 2, 3, 4. And if you launch this Mach-Zehnder interferometer, 2 by 2 Mach-Zehnder interferometer, it is actually constructed by 2 3 dB directional coupler, 50-50 directional coupler. WIDC means we just mentioned that it is actually wavelength independent directional coupler. That means it is a broadband operating about more than 100 nanometer, around 1500 to 1600 nanometer in C communication window. Similarly, another 3 dB bandwidth. Then what you have, this is a balanced Mach Zehnder interferometer. If you launch any wavelength, any power, then entire power will be coming in the cross port according to the transfer function. You know, this is a balanced Mach Zehnder interferometer. Transfer function you have learnt earlier also. Okay. If it is a balanced, then it is 3 dB, as if this 3 dB connected together. It is a longer directional coupler and it is used for cross coupling purpose. So, ultimately if you launch here, entirely it will be coming in the cross port. If you are launching here 1 milliwatt, maybe you will be getting 0.8 milliwatt, maybe 0.2 milliwatt will be lost because of the directional coupler, etc., but nothing will be there in the bar port. However, you know, if you have a phase shifter here, where thermo-optic phase shifter, in this case it is a titanium heater is deposited very close to the waveguide structure, and that has been connected to a aluminum contact pads through which you can actually supply some voltage. And because of the current, because of the temperature rise, if you can introduce a pi phase shift, then what happens, this power, entire power will switch over to bar port. So, you can actually switch power from the cross port to bar port. Okay. And since these directional couplers are designed wavelength independent, so any wavelength from 1520 to 1620, it has been tested that the entire power can actually, for all wavelength, you can switch by just giving pi phase shift. This is actually actual device fabricated in our lab, and also this is actually optical micrograph, it is shown, just photograph it is shown, Mach Zehnder interferometer. You know, this microheater length is 400 micrometer here. Okay. And if you see in the on state means what you get, you are getting in the heater is on. If heater is on, you are supposed to get everything in the bar port. You see entire wavelength, all the wavelength, this is wavelength region and normalized optical power output. On state, all the power will be in the bar port, and off state in the bar port it will be dropped. So, if you withdraw your current, heating current, then entire all the power will go here, and if you just switch on your current on state, then power will be in the bar port. So, this is how one can actually design a switch. Here similar thing already demonstrated. Instead of straight microheater, that means microheater deposited along the waveguide parallel to the waveguide, you can have a bend structure like this. It is also balanced 2 by 2, port 1, port 2 here, it is shown here. It is a fabricated device also, it is port 3, port 4, right. You are launching here P input, and this is the length, waveguide length here, and this is the waveguide identical length, only we have made a curved structure, so that your microheater also can be curved along the waveguide. So, now you can again apply voltage here. So, what happens if it is a curved microheater, we have seen that that is relatively efficient, because you know in the curved region it is somehow heat will be consolidated more in this region. Okay. In the straight region, it will be just straight portion of the waveguide will be individually per unit length, power dissipation and temperature rise will be whatever will be there. Here per unit power consumption, temperature rise will be more, we have seen. That is why bend structure is more efficient. We have just created a bend waveguide structure of 125 micrometer bending radius, and balance structure. There also we have seen that it is actually switching off state to on state. On state you are getting entirely everything in the bar port, off state entire wavelength spectrum, whatever tuning, whatever you can have experimental results, wavelength can be tuned, and you can see from 1520 to 1620 nanometer entire wavelength you can switch back and forth. So, using thermo-optic phase shifter integrated with a balanced Mach Zehnder interferometer, and if that Mach Zehnder interferometer designed with a 3 dB power splitter, which is actually wavelength independent, then that can be actually used for a very broadband integrated optical switch. That has been demonstrated and we have published here. If you are interested more, you can just download this paper and you can read, and it is very details, it is explained there. Fine. Now, Now, you see this is, instead of tuning your entire wavelength range, you just focus on only one particular wavelength. So, lambda equal to 1550 nanometer you are launching here. Now, if you just calculate the, you just send a current here or connect a voltage source, and you see depending on the voltage, as a function of voltage, you can actually control, if your current source, you can actually control the current, and if you know the resistance, then you know whatever the power consumed by the entire heater. So, if you just plot, if you launch here say lambda equal to 1550 nanometer, certain power you are launching here in this waveguide. Then as a function of consumed electrical power here, or power dissipated by the microheater, if you see that cross port and bar port, you see this is the cross port, power will be maximum and slowly it will go down and then it will be increasing. You see this triangle, they are actually experimental results, and the solid line, that is actually theoretical results. Theoretical results, extinction can be, it can be extinguished very high, but in practice and optical devices, you see we could measure up to minus 25 dB extinction. So, that means in the cross port, for example, cross port, whatever power is there, you can switch it down to minus 25 dB. So, it is about more than 20 dB extinction is possible. At the same time, when it is dropped in the cross port here, where that energy goes, you see that energy goes up in the bar port. This is the bar port results, we see that. So, that means we can say that it was the maximum here, somewhere here it is in the cross port maxima, and somewhere is the cross port minimum. So, if I just subtract this power to this power to this power, we can find that about 52.5 milliwatt power required, and that is happening, maxima to minima happening because of the pi phase shift. That means I can say that P pi equal to 52.5 milliwatt. So, that much power required to switch the power, electrical power, you need 52.5 milliwatt to switch power from cross port to bar port. If you withdraw that power, then again it will appear in the cross port, and that can happen for any wavelength. This is the experimental result evidence. Similarly, for if you just do similar experiment for bent microheater structure, where the efficiency or sensitivity is slightly higher, we found that actually the P pi, the maxima to minima happens, that is only in 36.7 milliwatt. So, it is because the heat is actually concentrated within a small region, and that is why longer length of the waveguide is getting higher temperature and phase shift will be higher. That is why you need low power consumption and for a certain temperature rise, and in turn your V pi, P pi, that means power required to get a pi phase shift is much lower, at least you can see that 1.5 times lower, okay, about 36.7 milliwatt. Good. So, now you see some more study, we have seen that we calculated back, because you know that P pi phase shift, you know delta phi equal to 2 pi by lambda times delta n effective by delta t times delta t, that is your delta n, multiplied by LPS. LPS known, del n effective by delta t known, lambda operation known, delta phi, if we are having pi phase shift, that means I can find out temperature rise. So, we need to know also, as I mentioned earlier, that you should be very careful that temperature rise should not be very high, so that that can result into a thermal crosstalk to another devices. We have found that two different type of things, this microheater, state microheater integrated in the balanced Mach Zehnder interferometer, and bent microheater also integrated with a balanced Mach Zehnder. What do we mean by balanced? Balanced means both the arms are of equal length. So, if you see that this curve corresponding to folded one, that means this one, and this one corresponding to straight one. If you are just plotting the delta Ts, steady state temperature rise, as a function of power dissipation per unit length, power dissipation, power thrown out by the microheater into the substrate per unit length, milliwatt per micrometer. So, for example, if you see, if you are using 0.04 milliwatt per micrometer, then the temperature rise in the curved waveguide structure, straight waveguide structure is actually lower, but the folded this one temperature rise will be higher. Same power, same length of the microheater. If you compare straight waveguide and bent structure waveguide, then temperature rise will be higher in the bent structure. So, that is more efficient. Okay. More temperature rise means more phase shift will happen. Okay. This plot is shown for the straight waveguide. It is somewhat experimental results, is following a straight line, that is what shown. And we have seen that the temperature rise, how fast it happens. If you just give a square pulse, suppose somewhere some square pulse you are giving, step function square pulse, voltage pulse you are giving here. Suppose here you are giving a voltage pulse. Okay. So, and then you monitor in a oscilloscope how fast temperature, when just voltage start from 0 to certain voltage, maybe 5 volt or so, then temperature rise will happen. You have to see how fast it is happening. You see, for straight waveguide and folded waveguide, the temperature rise, you see it is following same path as a function of time. So, it does not take much time, because per unit length, that is a physical parameter of the waveguide structures. How, what is the slab thickness, what is the waveguide width, how far the microheater from the waveguide, all those actually depends on your so called thermal constant, actually depends on, earlier we have discussed, you remember that, right. So, thermal constant, this depends on thermal capacitance and thermal conductance, that nothing to do with the architectural geometry of the device, but that thing actually, if you can actually engineer this thermal capacitance and thermal conductivity of the structure, then this can be actually engineered also. This rise time can be engineered. We have found that the rise time for both type of structure is about 5.1 microsecond, around 5 microsecond or so. Okay. Now, so this is the result. Here again, that you see, this is the voltage 5 volt, it is given directly from the oscilloscope, it is shown here, and then you see one is for the this is the high cross port and bar port, it is shown there. When cross port is reducing, bar port is increasing, reducing, increasing. So, you can actually switch back and forth between cross port and bar port, okay, and it is clearly showing that how fast it is rising, 5.12 microsecond, and falling also nearly identical 5.12 microsecond. Again, the details are given in this paper. If you want, you can download and then you can study. Now, next thing is that, well, we have shown that our microheaters P pi is in the order of say 50 milliwatt for straight waveguide structure, and for other type 37.6 milliwatt or something like that for bent waveguide structure. That means, bent structure is really effective. Okay. Earlier also it has been shown that the Mach Zehnder interferometer designed, balanced Mach Zehnder interferometer designed tactfully, then you can get a better efficiency. Not only better efficiency, you can actually, you do not need to go for very high temperature rise as well. Here if you see, this is a typical Mach Zehnder interferometer, and it is possible, it is like a type 1 type microheater. That means your waveguide and then oxide, and directly on the top of the oxide you are just depositing your microheater. This is the microheater. Okay. And what it is done, you have this upper arm and lower arm, you just make a spiral waveguide structure. You bring something like that, upper arm one type, and then you bring something like this. You bend spiral way like this, and then come back another way. Waveguide you define little bit longer like this, and come back like this. And this waveguide, in this case, in this paper they have explained, that is in 2009, they have created a spiral waveguide of length about 6.3 millimeter phase shifter length, and on the top there will be oxide, identical arm length. This is also spiral, this is also spiral, and then oxide is deposited. Top of it, microheaters are deposited but microheater is not like a straight microheater. Instead, there is a meander type microheater deposited on the top of the spiral waveguide. Okay, this is the microheater. So, you see the separation between two lines is 2 micrometer and width of the microheater is about 10 micrometer. This is spiral line and top 1.355 micrometer. And then if you are just applying voltage here, then current will pass through here and here, then all the heat I square R will be generated in this microheater, that will be actually directly will be radiating towards, conducting towards the waveguide from the top. Okay. That means your LPS now 6.3 millimeter long, and your all the power you are concentrating in this area, heating power. So, entire length is being actually affected, temperature rise can happen, right. So, in that case, since the waveguide length is very long and I know that delta phi phase shift is 2 pi by lambda, and then how much delta n refractive index change happening, and then LPS. Longer the LPS, you need lower the delta n, and delta n is what? Delta n is delta n effective by delta t delta t. This is fixed. So, delta n lower means delta t can be lower. So, you can have a very lower temperature per a desired phase shift, and they have shown that the waveguide length, okay, and if it is a straight waveguide, switching power requirement is about 35 milliwatt, exactly whatever we have got for our about bent waveguide structure. Our straight waveguide structure we have demonstrated, it was for 50 milliwatt, but here they are getting almost any waveguide length you need, the power required for switching is about 35 if you are using straight waveguide. So, straight waveguide, whether you use a shorter heater or longer heater or phase shifter, power requirement is same. Only thing is that how much temperature rise you are doing, that actually differs. Longer the waveguide phase shifter length, the temperature rise will be lower, but total power consumption needed almost equal 35 milliwatt. That is what it is shown, waveguide length. That means I mean to say that is a phase shifter. But if you are using spiral waveguide design like this, then waveguide length, if you are just increasing waveguide length up to 6.3 millimeter here, then power consumption per pi phase shift is exponentially decaying, and it is required very less amount of power. You see, it is about in the order of 5-6 milliwatt. So, from 37.56 milliwatt, you could reduce your power consumption, power requirement of about 5 times lower, 5-6 times lower, but at the cost of longer waveguide length, bit of longer footprint, and longer waveguide length. In turn, waveguide loss can be introduced, but if you have a low loss waveguide design, so whether it is a 250 micrometer or whatever it is 6.3 micrometer, maybe you can lose some power, optical power, but your electrical power will be reduced dramatically. Okay. But one thing is that since this is a type 2 heater is just directly on the top of the oxide, not directly direct heating like earlier we have explained here, that this device, this micro heater here, we have just, this is in the slab region. So, directly on the slab region heater was integrated, but in this example heater is just on the top of your waveguide, but above certain thickness of cladding oxide layer. So, that is the reason the thermal constant as you know, HW tau TH equal to HW by GW. So, the conductivity will be poor now, because oxide is cladded surrounding region. So, oxide, if it is poor, then tau TH thermal constant will be higher, and obviously they found that it is 14 microsecond thermal constant. So, that means switching time would be little bit longer in this case. However, your power requirement for P pi phase shift is much lower. Okay. So, that is a nice demonstration. There are many other type of phase shifters are available also, but within the scope of this courses I just restrict ourselves these two types of type 1 and type 2 only metal resistive heater. There can be, instead of heater deposition, one can think of that you have a slab waveguide, for example you have a slab waveguide, rib waveguide structure, and one region instead of metal deposition you can dope. It is a silicon. When you fabricate waveguide, that is intrinsic. Now if you doped p type or n type, then it will be conductor. So that there, through that, if you just send current also, then Joule heating energy also will be conducted, and temperature of the waveguide will be increased, and in turn you can get a higher refractive index change. So that is another type. Now we will be discussing thermo-optic wavelength detuning. So we have discussed how phase shift can happen, what are the figure of merit, and also we discussed using that type of thermo-optic phase shifter how one can design a Mach Zehnder interferometric switch. Now we would like to discuss how this thermo-optic phase shifter can be useful for wavelength detuning. We have already shown earlier that this delta lambda r resonant shift for a given wavelength, resonant wavelength, that is actually a delta Ng by n effect, sorry, delta n effective, I am sorry, this should be something we have derived earlier, delta n effective by delta Ng, group index of the waveguide. So that means this delta n effective actually proportional to the temperature rise, and if you just increase the temperature rise, a resonant wavelength will be shifted. So we have designed a all pass configuration. This is the bus waveguide, this is a ring, and then microheater bent structure. It's a titanium microheater again, contact pad aluminum here, you can pass current through here, and then I square R, it will heat up, then phase shift will be there, refractive index change will be there, and corresponding delta lambda r will be there. So in this case, this is the scheme, and after fabrication, if you see, this is the waveguide, this region it is shown here, zoomed region, waveguide region, and this is the microheater region, titanium microheater region, it is shown here. It is about 2.2 micrometer away. It has been kept with a safe distance, so that mode actually propagating within the waveguide, that should not be disturbed by the metal. Otherwise, if it is closer, then this field will be attenuated, loss will be higher. So we kept a safe distance 2.2 micrometer, and then since it is a slab integrated microheater, this is the silicon is there, that means you have a microheater here. So heat energy dissipated here, that will be conducted, and waveguide will be heated up. So three different type of device studied. D1, where quarter of the ring waveguide is cover up with the microheater, half, and this is almost 3/4. Three different type of devices we have tested, and we have shown here one particular device. All this type of, longer the length, you can have a lower the temperature rise. So that is what we tested, and we found it is established. And you see that for a ring resonator, if you see the transmission as a function of lambda, this is transmission according to the transfer function, that will be regularly coming like FSR. These are the resonance. Okay, this would be the resonance, and this one successive resonance separation is called free spectral range, and this particular micro ring resonator is giving a free spectral range of about 1.96 nanometer, 1.96 nanometer. Okay. So if nothing is given, no current is passed, then you see this black curve, this one resonance, it is shown around 50.5, this one one resonance, and next resonance will be this one, and this is actually FSR 1.96, this resonance is there. But if you flow current through the microheater, then it will heat up, then because of the thermo-optic effect, refractive index changes, and delta, the delta lambda r by lambda r, that resonant wavelength around 1550, that will be delta n effective, how much changed by Ng group index, and that will be tuned. If you are applying 0 voltage, you get this resonance and this resonance. Now you apply 5 volt, you see this blue curve, the resonance shifted, red shifted, you could tune. And then if you give 10 volt, then again shifted green curve. 15 volt it comes here, 20 volt it comes here. So almost entire FSR you could detune. Whenever you see the ring resonance, you get resonance here and resonance. In between there is no resonance. But if you can program it, you can tune to get a resonance anywhere in between two successive resonance all ready for passive waveguide. So that is how you can reconfigure. Okay. And also if you just position a particular, suppose you have this transfer function, this is your ring transmission, it is showing like that, and then if you have a laser, this is the wavelength dependent transmission, right. And if you are just putting a laser here, laser wavelength here, operating wavelength lambda is given, operating lambda O is given here. Now, if you, what you can do, if you can tune your resonance by means of microheater, then your transfer function will come like this. So, originally your laser light would see high transmission, but whenever your resonance tuning this side, then it will be seeing the low resonance, low transmission. So, that means you can get certain kind of intensity modulation, intensity switching. So, that means you can make on off of that particular laser, high low you can make. So, that is what it has been shown. For a given wavelength, you are just operating a particular lambda, and this lambda, for example, lambda operating is actually say greater than lambda r, certain resonance. Now, you see whenever some voltage is high, then your transmission is high. Now, voltage is lower, that means heating current is lower, transmission drops. Okay. So, again that way actually you can tune. Probably whenever voltage is there, that means you are getting high, that means it is other way, that means your, if it is your transmission is like this, in this particular example, this is your wavelength lambda, this is your lambda r, and suppose at exactly you match your lambda operating exactly to lambda r. So, that means whenever no voltage is there, your transmission is lower, because that region, that particular operating wavelength will be stored in the microring resonator. Now, apply some voltage, so that this can be tuned here up to here, your microring resonator resonance tuned here. So, that means your this particular operating wavelength, now it will see maximum. So, that is why when you are just on, then it is maximum transmission. This is optical and this is the voltage source. So, here voltage source you are giving that signal pulse, you are giving pulse like this, and then your optical output here, that also will go according to your pulse. So, you can get switching, on off switching you can get. Okay. And Thermo-Optic wavelength detuning you can get, as well as switching also you can get in a microring resonator just by integrating a microheater. Okay. You can make it active. Cool. So, here I stop that. Okay, Thermo-Optic related phase shifter and switching and detuning, everything discussed today. Next, another type of tuning of integrated optical devices, particularly silicon photonic devices, is very much popular, that is called plasma dispersion effect. That effect, how it can be useful and how it can be better or poorer than the Thermo-Optic phase shifting, Thermo-Optic switching or Thermo-Optic detuning, that will be discussed in the next lecture. Thank you.